Today, I'm going to talk about credit risk. I'm going to give you an introduction to credit risk. It will be followed by another treatment of credit risk next week. That will be more practical. Today, I want to focus on some of the fundamentals of credit risk. I want to start telling you about a case. Some people say this is how credit risk really started, more than modern credit risk, how it really started. We will see. It has to do with with a very famous interest rate swap between essentially two companies, Goodrich and Rabobank, in the year 1993. I will start telling you a little bit about these companies. Goodrich, you probably know. It was a fairly well-known tire manufacturer in the 80s. They have evolved in their business plan. Now they do military stuff, aerospace manufacturing. They have done PVC equipment and stuff like that. But back then, they were predominantly a tire manufacturer. So cars and trucks, tires. And the other character in this discussion is Rabobank, a Dutch bank. It's actually part of a very large financial conglomerate. And what gave rise to this were the financial difficulties that Goodrich had in that year. Now, Goodrich was not alone. 1983 was a pretty nasty year. You should know that in the year 2008, that you may have a better memory of, or better knowledge of. 2008 was for a long while, compared to 1982. The question was, is 2008 better or worse than 1982? 1982 and the year that followed, 1983, which is when this swap happened, was a year of very severe recession with very high interest rates. So in the case of Goodrich, this created for them a double whammy. On the one hand, interest rates were very elevated at a rate of 11%, and the country was in a recession. So you can imagine how severe that was for car sales, and in particular tires. So that the situation was very dire for Goodrich, and Goodrich was looking for a $50 million financing. They had a line of credit with the bank. They preferred to look for external financing and not use the line of credit. As we have learned, it's better to always use someone else's money. So if you have a line of credit, you prefer not to touch it and try to find financing in a different way. On the other hand, Rabobank was financially very strong, and one of their businesses was they managed the pension for Belgian dentists. Now, when you manage a pension, you are in search of a variable rate yield. Pension plans, they need to stay on par with inflation. So when rates are higher, they need to have higher return, and when rates are lower, they can afford lower return. They were looking for a variable rate yield on their assets. Okay. Now the situation was that when Goodrich went out, Goodrich is going to be the main character in this story. When Goodrich went out looking for financing, this is what they found. They found that they could get a fixed rate at 12.8%. Note that floating was at 11. Okay, so but they could get a fixed rate at 12.8%. They had just been downgraded to BBB minus, and when you're downgraded, not only rates go higher, but a fixed rate goes even higher. Whereas a Rabobank could access the AA rate, which was 11%. So much cheaper for Rabobank, obviously, because Rabobank had a better credit rating. Now, the interesting part is what happened if you go to the floating rate. On the floating rate, Goodrich was able to get a better deal. They was able to get a floating rate that was Fed funds plus 50 basis points. And Rabobank could get a Fed funds, and that was about it. Okay, so let's say that Fed funds was at 11% to simplify our discussion. So we can see that because Goodrich wanted a fixed rate loan, they would have to pay 1.8% in excess. Actually, sorry, 1.3% in excess of what they would have been able to get if they wanted a floating rate. Okay, so this is a typical situation. It happens to me when I go shopping. What I like is more expensive than what I don't like. Okay, and that was the same for Goodrich. The interesting part is that Rabobank didn't care. Rabobank could get practically the same price if they went fixed or floating. The spread was about zero. And they had a common consultant. I believe it was Salomon Brothers. I'm not sure. I think it was Salomon Brothers. And the consultant knew this. And the consultants saw an opportunity to profit from this situation, as you can imagine, right? Imagine that I go and try to buy something which is expensive and I really like it. But it's expensive. I could buy something else which will be cheaper. But for you, they both have the same price. Then what the consultant suggested is that they would just swap it. They would get what they didn't want and they would swap the prices with each other in the following way. Okay, I'm going to give you the schematic description of what happened. So Goodrich went out and got the floating rate loans that they did not want but were cheap. So they made some arrangements with some pensions, I believe, or no, savings banks, to borrow from them at a floating rate that was Fed funds plus 50 basis points. And they were going to pay these payments on a semi-annual basis, not too relevant for our discussion. And Rabobank was going to go and get what they did not want, which was a fixed rate asset. They were going to get a fixed rate income from fixed rate products in the euro dollar market. That's where they were interested in. And then a trust was created. A trust is essentially a fund. It's a special purpose vehicle that is created to do financial transactions. And in this case, the financial transactions that Goodrich and Rabobank were going to do was as follows. Goodrich was going to exchange payments with the trust in the following way. Every 6 months, they're going to receive money from the trust that was Fed funds minus a haircut, minus a certain discount, which is what they needed to pay their loan from the U.S. savings banks. And in return, they were going to pay a fixed rate to Morgan that was equal to 11% per year. To understand the deal, let's ignore the payment structure, whether it was semi-annual or annual. Okay, let's ignore that. This is the way it was, not too important for our discussion right now. So as you can see, the net effect of the floating rate loan and this interest rate swap for Goodrich is that they would end up with a fixed rate loan of essentially 11% plus 5 plus 50 basis points plus X. That's essentially what they were going to get. Understand? So they got what they wanted. They got a fixed rate loan paying a little bit more than the cheaper product that they were quoted, but less than they would have paid if they got a flat out fixed rate loan. Understand? Okay, let's continue because we're going to get all the economics of this transaction. On the other hand, Rabobank was indifferent, but was offered to get their fixed rate instruments and then swap it with the same trust at the following rate: 11% fixed. That's what they would receive, so they can pay their obligations on the other side, and they were going to put into the trust something equal to Fed funds minus a certain Y that I'll talk about percent on a semi-annual basis. Okay, so as you can see, there's two interest rate swaps on both sides of the trust, one with Goodrich, one with Rabobank, that would have exactly offsetting payments. In fact, they would actually make some revenue for the trust if the number X is bigger than Y. Everybody sees that? If X is bigger than Y, the trust is going to make money. If Y is positive, Rabobank is happy because they're getting a discount. They're making a little bit of money. They're making Y. All right. And Goodrich, as long as X plus 50 basis points is less than 1.3, they would be happy too. Okay? Everybody sees that? So this is a very interesting opportunity to, if this works, then this is a way to make money. I told you that working for free is finished in this course. Okay, now we're going to study situations where money is to be made. And the economics are roughly this. Let's say that it's a $50 million loan. It went for, I think, 8 years, not relevant. But if you look at the diagram, there's essentially 12.8 minus 11.5% to be made for free, to somehow be spread amongst Goodrich, the trust, and Rabobank. See that? 12.8 is what Goodrich was. So at 12.8, Goodrich would be indifferent. If they can get a deal better than 12.8, they will be happy, right? But the differential for Goodrich encouragement to get involved in this is 11.5, because that's the lowest they could pay. And that the difference is about 1.3%, which on a $50 million loan is about $650,000 per year. So this is the amount of money you can make for free, $650,000 per year. So let's see how each party makes money out of this. On the one hand, Rabobank makes Y%. That is what they would make based on market prices and this particular deal, right? They will have to make payments into the trust, which are going to be Y% less than they would have to pay to their outside counterparties. The Morgan Guarantee Trust would make the difference between X and Y. And Goodrich would save 1.3, that was the original differential, minus X minus Y. So as long as X plus Y is less than 1.3, then they would make money too. So now the case somehow ends here, because now this would be the time for everybody to make a deal. If you think that the $650,000 should be split equal ways amongst all three players, then you divide it by 3. Y would be essentially 200,000. X minus Y would be essentially 200,000. So X would be 400,000. And then Goodrich will save $200,000 per year. That would be a way to approach it. Okay. Now I'm not going to get into the negotiations of this. One of the things about not working for free is that the question is how much you charge for what you do, right? So the charging of this is something that we will see later, probably next week. But for today, I want you to understand the basis of how these types of deals happen. Now, this is a nice case in perhaps in structured finance, or not even that, maybe in corporate finance. This is very simple. My interest in this is to explain the credit aspects of this, because this is a credit instrument and credit risk is what's happening here. So for that, let's analyze again this situation. Note that the only credit component to this deal comes from Goodrich. Rabobank has very good credit quality. No, that was not part of the credit discussion. So let us focus on Goodrich for this particular deal and understand what could go wrong and why someone should make some money. Okay? So first observation, what happens if rates go up? If rates go up, I would expect the Goodrich credit quality to go down. Why? Because if rates go higher up, sales will go further down. So its credit quality will get worse. Okay? Now, from the Morgan perspective, from the trust perspective, is that a good thing or a bad thing? If rates go up, this is a good thing for the trust. Why?
Is it because the federal rate goes up?
Okay, if if rates if rates go up, it looks like the trust is in trouble because they will have to pay more to Goodrich, right? But don't forget that what they pay to Goodrich is coming from Rabobank, no matter what. So the trust doesn't care what they pay Goodrich. The only fear the trust has is that Goodrich does not pay, right? But if rates go down, sorry, if rates go up, Goodrich doesn't have to pay anything to the trust. The trust has to pay. You're very happy to pay a bankrupt counterparty. You're not happy if the bankrupt counterparty has to pay you because they're not going to pay you. You understand? This is the change of logic that credit has with respect to market. I repeat this again, this is very important. If rates go up, Goodrich is more likely to default. Goodrich could go bankrupt if rates go way up. But what if Goodrich goes bankrupt and you have to pay Goodrich? You're happy to pay because you get the money from Rabobank. See? It will be very bad if Goodrich has to pay you and they go bankrupt. That would be bad. But Goodrich going bankrupt and you have to pay Goodrich is okay. You get the money from Rabobank. You see that? Okay, let me continue. What happens if rates go down? Well, if rates go down, then Goodrich will have to pay you. And then you hope they pay you because you need the money to pay Rabobank. But if rates go down, you expect sales to go up. So Goodrich should not be in trouble, should be okay. This is credit risk thinking. This is what gave this swap a low credit risk profile. Note that the swap has no market risk. It has a credit risk, and this has a low credit risk profile. That's why it happened, and that was considered to be one of the examples that explains very well the nature of credit risk. Okay? This is what we're going to be dealing with today. Things like this. Is this clear? It's perhaps a bit counterintuitive, right? That we are happy when we have to pay. And the reason is because credit is different from market. In market risk is when your portfolio goes up and down in value. But credit is when your counterparty doesn't do what they're supposed to do. So if Goodrich goes bankrupt, you prefer to go bankrupt when you owe them money, not the other way around. All right? Okay, think about that, okay, if it's not clear. Now, let me tell you credit risk. So this one's in 1983. I'm going to jump to today. I want to show you how credit risk is today because it's very different. Credit risk has evolved a lot in the last 40 years, a lot. And I'm going to explain this with a deal, which was a real deal. And it's for me, it's the best way to explain what's going on without giving you a lot of theory. And it has to do with Scotiabank. Scotiabank, you probably know, did a deal with a Chilean supermarket. It was the name of the corporation that owned the supermarket was called Cencosud. Okay, it was a Chilean supermarket. You may know that Scotiabank has a big business in Chile, Peru, Colombia, and Mexico. It's our most Latin American bank in Canada. Okay, this was just part of that. So I have the news clip from here, what they did, and you can also ask ChatGPT. This information is available. I'm not going to tell you anything that is confidential. I don't think. I hope not. I will try not to. And the deal was as follows. The deal was as follows. The this supermarket chain had a program very much like President's Choice. Loblaws has a program in Canada, or some of the other retailers have a program of a loyalty program or a customer profiling program. And according to that, what they were offering their customers, this is the customers of the supermarket, but it was a Scotiabank product. What they were doing is, when a customer went to pay for their, groceries, they could ask for a loan on the spot up to $300, I believe it was. And then if you ask for a loan as you're paying for your groceries, then the following chain reaction happens. The supermarket has to somehow communicate with Scotiabank. I don't know the details of that. Then Scotiabank has 5 seconds to decide if they give the loan or not. And if they give the loan, they notify the supermarket within 5 seconds, and then the supermarket gives the loan to the customer. You understand that? Well, that's credit. That's credit risk too. How is it different from the Goodrich deal? You may think it's different because well, there's several differences. One is, $50 million is not $300. That's one difference, but that's just perhaps a number. Another difference is that it seems that Goodrich has a lot of information. Goodrich is a company. It's traded in the New York Stock Exchange. It publishes financial statements every 3 months, gets audited every year. It seems that you know everything about Goodrich. And it seems that if a random person just shows up and asks for a loan at a supermarket in Chile, you know nothing about that person. That seems to be the difference, right? Well, 40 years ago, that was the difference. But as you know, today, that is not the difference. In fact, today, you probably have more data about a random shopper in a supermarket in Chile than you do about Goodrich, right? Because of the ubiquity of these loyalty programs, which are really nothing but a way to extract information and do customer profiling from your customers. So that's perhaps now there's two considerations to do here. One is a consideration that has to do with the technical aspects of that, which I will describe very, very succinctly. But the one that I'm more interested in is the business aspects of that. And the business aspect of that is, imagine how good this was for Scotiabank, because with essentially with this deal, Scotiabank became the third largest lender in Chile overnight, and not one branch, no staff. You see how good this is? This is very smart, right? This is very smart. It also had some other regulatory advantages. I'm not going to get into this, but I want you to understand that the opportunity for business here is very, very good. So this is the business aspect of that. Now, I told you what made this deal happen is the fact that today we have this ubiquity of the data. Data seems to be everywhere. And by data, in this case, is metadata, right? This is something that happens very general in the industry. This is just a particular deal, but just about every company is cross-referencing data coming from different business lines, and this is part of how they become powerful. I should say in this regard that one of the Loblaw, the Loblaw company that owns Loblaws, Shoppers Drug Mart, and President's Choice Financial, is one company in Canada who is they are building, or probably have built already, a data scientist campus in Brampton. They were going to hire 200 people. They approached me a while ago because they were looking for people. If any one of you is interested in applying, please do so. Okay, mention my name or even tell me, and I'll be happy to make the introduction. In fact, one of the people who took APM466 a few years ago is working there. You can find her profile on LinkedIn. Okay. This is what's happening. This is the new credit risk. And in this case, supermarket shoppers, they voluntarily give information to the supermarket. The bank could have different information. For example, in the case of in Canada, President's Choice Financial, the bank, and the Optima card of Loblaws, they share the information. This is what you give them. This is how they profile you, and that's how they know what's going on. They know your shopping patterns, for example. In the case of Chile, it was a big deal. If you apply for a loan and your customer profile, you say, for example, that you are a doctor and you make $100,000 a year or something like that. That will give you a good quality. Well, the supermarket will have a way of checking if that is a suspicious statement. They know where you shop often, so maybe you don't live where you say you live, or maybe the things you buy do not correspond to your stated profile. Or this is what data does, right? Now, I don't have to tell you how to analyze this. You already know. So this is not going to become a course in data science. That's why I'm just going to give you this information, but then I'm going to go back to the Goodrich case, because that is going to be more useful to us to understand how credit risk is put together. But I want you to know that today, credit risk becomes an exercise in data analysis. And you have to obtain information from data sources that help you with credit, but also help you enhance the business and produce risk systems. And we're transitioning from a risk-based to a rules-based system. This transition is not something I'm going to discuss in this course, because then my course will become a course in machine learning, and you already have taken enough of those, I believe. Okay, so I'm going to stay with the finance, but I want you to interpolate between what I will be doing today and the machine learning data science so that you can see what's happening between the credit considerations we'll do today and all of the data analysis you can do with everything you've learned. I hope that's clear. Okay? So, so the consequence of this is that credit risk today becomes an exercise in data management, dealing with very disparate data sources, doing the analysis of that, and then drawing conclusions that would be based on the credit risk discussions I'm doing today. So I'm going to focus on the finance, not the technology. Okay? I know you know the technology, so let me talk to you about the finance. And this is how I start this course. I'm going to talk about credit pricing first. Okay? Is that clear? All right. So for that, I'm going to show you how to do cash flow valuation. I'm going to show you how to do default probabilities, what they mean and what the context for that. And eventually I will get into the credit process. Now, some of these things will be done next week. Today, there will be a natural end for what I want to do. And then I will continue with something else and the commercial models, which I will do next week. So this is a rare situation in which my course somehow has a spillover into next week. Usually I like my courses to be monographic, but today, because this is such a vast area, there will be some stuff that will go on to next week. So I'm going to start with very, very simple cash flow valuation. In fact, I want to start the same way I started the course back in January. Exactly the same. I remind you that the way we started this course is by pricing cash flows. If I have cash flows in the future, I know how to value them today. You are experts at this because, amongst other things, you've done assignment number 1. Okay? Which was the creation of the curve R in this expression. So I'm talking to experts, I know that. So because I'm talking to experts, I want you to realize one thing that we have not considered. If we go back to January, I remind you that here we had N is the number of payments, P is the amount we pay at time T, the spot rate is what you calculated in your assignment. But in January, we assume that every payment happens with probability 1. What we're doing today, we're removing that. What if these payments happen with probability less than 1? That would be the way to start credit risk. And now we're going to make a connection with everything we developed back in January, okay? You see what we're doing? So this should be very familiar territory for all of you because you're all experts at this. All right. Now, if each payment has a probability of defaulting, which is bigger than 0, or a probability that is going to happen, which is less than 1, if there is a probability of solvency, which is non-trivial, then one might think that the cash flow valuation should be adjusted as follows. I should multiply each future payment by the probability that the payment will happen. Right or wrong? Right or wrong? Is this intuitive?
Would it be wrong because you might have like it's not independent if one fails, the bond fails, like the rest of the bond fails. You can't just have like one missing payment.
Okay, so that's a very interesting comment. I will be addressing that in a little bit, okay? But I want to address another objection I might have besides yours, which is in the 33-cent game we learned that it's very dangerous to price objects, financial objects, using probabilities. Didn't we? Am I doing the same? Am I saying that pricing an instrument or a cash flow series using probabilities that the payments will occur will lead to the same mistake we made when we priced the 33-cent game with 50 cents? Could it? The answer is yes. But I don't want to deal with that right now. We've spent way too much time on option pricing. So let me just say, and because we're experts now at all of this, let me just say that this will be true if the probability that my payment happens is risk neutral. How's that? We've learned that too. So let me not deal with that. In fact, this could be a very nasty discussion because this might be an incomplete market and then we don't know. And so I don't want to deal with that. I'm just going to say that this would be true if my probability of solvency is risk neutral. We will see what that means later. Let me put it aside for now, knowing that you know what I'm talking about. Okay? Okay, so this is true with a caveat. The probability of default of solvency or default should be risk neutral. We will see what that means later. Now, if we look at this expression with our understanding of fixed income mathematics, then what I can see is that as the probability of solvency decreases, if the value is the same, the payment should increase, and that's what happened with the bad quality loan. You have to pay higher coupons to maintain the value of the bond. Okay, and the increase is essentially the inverse of the probability of solvency. So that would lead to what's called a credit premium. We'll see that in a bit more detail in a minute. Okay. Another possibility is that if the payments remain fixed, then the value of these cash flows would just decrease as the probability of solvency also decreases. Okay. So this is the obvious symmetries that one observes in this expression. Okay. Now, risk neutral pricing, I mentioned that earlier, right? If the risk neutral pricing is to be followed, then I need my probabilities to be risk neutral. For example, implied by market prices. That's the way they will be most of the time. So we don't have to worry about that too much. Because most of the time, you will see when we calculate default probabilities, we don't have statistical methods to calculate default probabilities. What can we do to calculate default probabilities? Looking at how often you have missed payments doesn't work. We're going to see that default occurs only once. Once you go on default, you stay on default forever. Okay, we'll see what that means in a minute. So we cannot rely on time series or statistical analysis to get probabilities of default. We have to, almost by design, the probabilities of default we will come up with will have to be risk neutral. Just watch, okay? One of the difficulties in credit is that defaults only occur once. And then once you default on your obligations, essentially the counterparty that defaulted ceases to exist. They may make some, they liquidate their assets, the company's over, and then the recovery rate that creditors have comes from the liquidation of the assets, and the company is finished. That doesn't exist anymore. So we need a different way to measure the probability of default or the probability of solvency. And a key to understanding that is the following construction. I am going to introduce my first mathematical construct of the day. It is the hazard rate or the credit spread. Because I know that the probability of solvency is between 0 and 1, I don't know what it is. It cannot be more than 1. It cannot be less than 0. It's a probability. So I'm going to take the logarithm of it. I'm going to hit it with a negative sign to make it positive. And I'm going to divide it by the time at which I'm calculating the probability of solvency. And this is a definition. I don't need to justify it for now. It's a definition. It's going to work. So it's a definition with hindsight. I'll show you the hindsight in 2 seconds. Okay? So this is a definition, and this is the hazard rate. And it has the property, and this is the hindsight, that if I use the hazard rate into my cash flow valuation formula, notice that the probability of solvency is the exponential of h times t, negative sign. So I can absorb the hazard rate into the exponential, and what happens is something remarkable. It's exactly the same cash flow valuation formula from January that we saw in our very first lecture, exactly the same, where we are adjusting the yield curve with this newly found mathematical construct. Now, this is very good news. This is very good news because remember what you did in your assignment number 1. What did you do in the assignment number 1? I gave you Bank of Canada and I asked you to calculate the yield curve, and you could do it, right? All right. Imagine I ask you now, so go back to your code and get me the yield curve, not for the Bank of Canada bonds, but get me the curve for, say, Bell Canada bonds or TransAlta Pipelines bonds or Highway 407 bonds. Get me those. What happens? The same code you did will give you a curve, will give you the curve of those corporations, right? The same code, you don't have to do anything. Just put the data for a different bond. Those curves will be strictly above the curves that you calculate for the Bank of Canada bonds. The difference is the hazard rate. The difference would be the probability of solvency. In fact, if you have the probability of solvency, you have the probability of default. So your assignment number 1 will give you the probability of default of all those companies, right? And it's a probability of default which is risk neutral because it's the one that prices the bonds. See that? This is the advantage of being an expert, right? You're experts at all these things. So this is all, you just need to put all these pieces together. That's how powerful you have become in the first 2 months. I want you to be aware of that. Okay, you should feel powerful now because everything we have done happens to be relevant when we're doing this. And you can actually run the numbers yourself even. You already have your library written down and ready to be deployed. I should tell you that assignment number 2 will be related to that. But I'm not going to tell you what it is yet, okay? It's not going to be a repetition of assignment number 1. You will have to use assignment number 1, but it's not a repetition. No. It'll be something new. Okay? All right. So this hazard rate is oftentimes called the credit spread because it adds a certain percentage to the yield of your counterparties. And the worse credit quality the counterparty has, the higher that credit spread is going to be, and the lower the probability of solvency of the counterparty. Okay? All right. I have a question here. It's an exam question. I hope it's well, it's just an exercise, just to sediment what we have learned. Okay, we've climbed this hill very quickly, and the reason is that we have lots of machinery now. So we're not walking; we're just driving our super truck, right, up this hill because everything we have learned so far. So imagine I give you here. This is the question. I have a senior unsecured double B rated bond that matures in 5 years and is paying an annual coupon payment of 6%. Okay, so this is a bond like what we have seen in the past. And here, obviously, people typically, not us, but people typically, they use annual compounding, non-instantaneous compounding, not important. And this is the table given to us of the 1 year forward curves. 1 year forward curves for each credit rating. So we see there the credit rating curve for, we see there the yield curve for the credit rating double B is right there, okay? And using this table here, we need to calculate the 1 year forward price of the bond if the obligor stays at double B. How would we do this? So I'll just walk you through something very, it's a simple application of what we have done. So if matures in 5 years and is paying an annual coupon payment of $6, what we do is we just discount the coupon payments and the final payment with the curve that's given to us by the table. The table is giving us a curve, and that's what the curve is. We discount it using annual compounding, and that's the answer that we're looking for. It's just over $102, okay? So easy to do, things that we have seen. That row in the matrix gives us the discount factors of the future payments. Okay. All right, so let me climb to the next hill. I'm going to give you the basic credit. It's the simplest model, but it's going to be so basic, it's going to give us quite a bit of intuition about what's happening with credit markets. I'm going to make an assumption, which is my counterparty can only be in one of two possible states, solvency and default. Obviously, you can think that this is true for everybody. You're either solvent or on default because there's nothing in the middle. But I'm also assuming that the probability of default in a given period, say a year, is constant over time. Okay, it will be the same. Your probability of default in the next year is the same as the probability of default 10 years from now for the year after year 10. Okay, I want to assume that it doesn't change. So you don't get better, you don't get worse. In other words, I'm saying that the probability of being solvent at time t plus 1, conditional on being solvent at time t, is constant, equal to a number q. That's my assumption. That's my model. Okay. So in that case, what's the probability that I am solvent 2 periods after is q squared. What's the probability I'm solving 3 periods after is q to the power 3, right? And we can generalize this by saying that then the probability of solvency at time ti is that fixed number to the power ti. Typically, the definition of Q is the probability of solvency in a year. So if T is written in years, this expression is exact. That's what this very simple credit model is doing for me. In that case, if you go back to the definition of hazard rate, I save you the work, I'll tell you what the answer is. The logarithm of Qi is T times logarithm of Q. The T's kill each other, and what you get is that the hazard rate is constant, does not change with time. This is fantastic because I can restate my model by saying that I am dealing with a two-state Markov model, okay? And only two possible states, solvency and default. And then the transition probability matrix of this Markov chain is given by what is written here. The transition from solvency to solvency is the number Q, is the probability of solvency is constant. The transition from solvency to default is 1 minus Q, as it has to be. The transition from default to solvency is 0 because with a 100% chance, if you're default, you stay default, okay? Now, at this point, I need to ask, it's a bit of a rhetorical question, but I need to ask if everybody is familiar with Markov chains. If someone is not familiar with Markov chains, please write something on the chat. I need to know. I am going to explain Markov chains to you today, and I just want to know how fast I should go in that explanation. So if you don't know what I'm talking about when I say a Markov chain, please say something in the chat so that I adjust my speed as I lecture. I'm going to check the chat now. Okay. So 2 people say they're not familiar. I don't know how to extrapolate that, but so what I will do is I will explain them to you. I will just go a bit more slowly. And for the people that have never seen before, pay attention. You may have to complement this with some primer or Markov chains, but I hope today I give you everything you need, and certainly the motivation to go and learn Markov chains. They're not that hard, okay? They're not that hard. Okay, so I'm going to go a bit slowly when I explain that. But let me use this example, perhaps to remind everybody what a Markov chain is. So a Markov chain is a very simple situation, describes simple situations, describes a stochastic behavior. And in this case, let me go to what we're doing. What we're doing is we're saying, I can be solvent, I can be on default. The probability of being solvent after I was solvent a year ago does not change over time. It's always the same. In other words, let's say that the probability that I go bankrupt in a year is 7%. And it's 7% this year, next year, 10 years from now, after I retire, it's still 7%. If that number doesn't change, then you're dealing with a Markov chain. This is a very simple one because there's only 2 states, solvency and default. You can have Markov chains for everything. You can have a Markov chain that describes where you are. The probability from being in this place going to this other place is always the same. That's a Markov chain. And then what you need to know is the probability of going from anywhere to anywhere. Or in this case, because we only have 2 states, we need to know the probability of transitioning from one state into another. There's only 2 possibilities. So we're transitioning from solvency to solvency, Q, solvency to default, 1 minus Q, or default to solvency, 0, or default to default, 100%. So this is what a Markov chain is. We're going to see more examples of Markov chains today. So I hope this is enough for those who have never seen Markov chains to see that when it comes to this, I'm just talking about flipping a coin. A coin flip, a sequence of coin flips is a Markov chain. Very simple one. You have heads and tails. And the probability from heads to tails tells you it's 50% always. So that's a trivial Markov chain, but it's still a Markov chain. Okay? All right. So I'm going to and a way to say my previous result is to state it saying that a two-state Markov model for credit gives a constant hazard rate. I haven't done anything. I'm just expressing in mathematical terms the previous expression that we derived earlier when I had not even mentioned the word Markov chain. Okay, so at this point, a Markov chain becomes just a vocabulary term for a while. Okay? Okay. If anybody has any trouble understanding what I'm saying, because I may use any quantities from Markov chains, please raise your hand, unmute your mic, and say something, because everything I will do today is very easy to explain without Markov languages. Okay? All right. Now, so if you look at credit spreads, and everyone you can calculate the credit spread for any company with a bond. You can do that. That's your assignment number 1, right? You would typically see that there's something like this. I just made this up. They're clearly not constant. The spread is not constant. That means that my credit model, this one, which is very simple, is not accurate. Okay? Which is okay. It's okay. I'm still going to use this model to develop an intuition, some way for us to think about credit. But when it comes to getting numbers, we will have to use a model which is better. So just to show you how useful it is, let me do an application of what we have learned to understand sovereign risk. Sovereign risk is the probability that a country defaults. This comes up in the news very often, right? I don't know how much you follow the news. You should follow the news, by the way. That's a good piece of advice that I give you. Follow the news. Read Bloomberg. Don't read don't get your news only from Reddit or something like that. Read the mainstream media channels, because they will help you get a job. Okay, and it's to understand not so much what people think, but it's to understand what people talk about. It's just as important. Okay, so you probably know a country that has been in the news often enough about sovereign risk was Argentina, for example. Argentina is a country that every decade or so needs to default on their debt. They cannot pay their obligations. Every so often, we are hit with the news that there is a chance that the United States may default on their debt. In fact, you probably know that this year they have a lot of debt come due. And by a lot, I mean a lot, like $10 trillion or something like that. So they're going to have to refinance that. And to refinance that in the United States, they need congressional approval. And oftentimes, the congressional approval comes a few minutes before there's a deadline for that. So, a mishap could happen. So, sovereign risk is something which is very ubiquitous. And we have had situations in which countries have defaulted. So let me get into that, what we have learned so far today. Again, we're powerful. And I'm going to use Greece as the example. The reason I'm going to use Greece as the example is that in the year 2015, something remarkable happened in Europe, which is going to be very useful for my discussion now. It's a business case. It's a very useful business case. Europe, as you know, has a single currency. Every country issues sovereign bonds in the same currency. Now, that's different from North America, for example. Canada, United States, Mexico, we use different currencies. If all the countries issue the same currency, then you can compare the yields of one bond and the yields of another bond. It will be very difficult to compare the yields of Canadian bonds with the yields of US bonds or Mexican bonds. Why? We all use different currencies. So a lot of the differences in the curves, you don't know if they are due to currency issues or credit issues of the country. But in Europe, we don't have that because the currency is the same. So you can compare. It's very good for this course, Europe. And in the year 2015, there was one country that was put on the spotlight. That was Greece, and I don't know if you remember or even you heard. You must have been very young, but there was this term coined that was called Grexit. That was the possibility that Greece would leave the European Union, would leave the euro as a way to perhaps not default on their debt, translate all the currency into drachmas, and then just pay drachmas to the people by devaluing the drachma currency, which they could not do with the euro. Okay, so that's the context in which I'm going to give you this particular case. We're going to get some very interesting conclusions with our very rudimentary credit techniques that we have developed in an hour, and your assignment number one, okay, in combination. So I'm going to use that as a way to explain what I'm talking about. So let's try to model in a very simple term, in the simplest possible term, the situation of a country that has some debt issued. So this is a notional. Okay, we just mentioned the United States will have to refinance about $10 trillion worth of debt. So that's the notional. Okay, how much debt you have to refinance or finance. Then there's the probability of solvency, which we now know is going to be risk neutral because it's coming from bond prices. So there's the probability of solvency after 1 year. I'm going to assume that that this probability of solvency is constant. In other words, I'm going to assume that default is a Markov chain. Note that it cannot be a Markov chain with only two states, which is what I'm saying here. That's the oversimplification I'm doing. Why not? No one is talking about Grexit anymore. No one is talking about Greece leaving the euro. Something must have happened. Well, whatever happened is inconsistent with my assumptions here. My assumption here is that nothing changes. Okay? But it's a good assumption to get heuristics. It's a bad assumption to do numbers, but it's a very good assumption to understand things, as you will see. Okay, so I will assume that this is a Markov chain, although it cannot be a Markov chain with only two states. Maybe with more, but not with two. Okay, now I need to introduce to make this realistic, I need to introduce a concept I have not discussed yet, but I want to introduce it now. This will be a very important concept for us next week. We will have a model for this next week. Today, I'm just mentioning it, and that's the concept of recovery. When a country defaults, actually when anybody defaults, typically creditors don't lose everything. Okay, it's not a all or nothing payment. The cash flow valuation formula I described earlier is incorrect. Or sorry, not incorrect. It's correct. It's an oversimplified version because it assumes that if there is default, there is full default. Usually that's not the case. There's some partial payment. It's called recovery rate. And recovery rate is measured with one number, which is between 0 and 1, which we don't know. Recovery equal to 0 means you lose everything. Recovery equal to 1, you actually get everything back. So it was not a real default, right? On average, R is about 50%. On average, but we'll talk about that next week. Okay, so, but it's a number. It's a number. Let me take that into consideration to get a realistic description of sovereign risk within our very simplified context. Let's assume R is 50%. Okay, so let's see what happens with the bond. I want to assume that my bonds are zero coupon bonds, no coupon payments, makes things easier, okay? And then I can then adjust our cash flow valuation formula to take into account recovery because I have the event of solvency with probability Q, in which I get my notional back. The value today is the discounted value of the notional. And then I have okay, so that's the part with the no default payment. Yes, I'm multiplying the probability of default, risk neutral. Sorry, the probability of solvency, risk neutral, times the discounted value of my payment. But then I have the default event. In the case of default, which has probability 1 minus q, I get something back. I get a proportion of what I'm owed back. And the proportion is given by R, the recovery rate. Okay? So these two terms is a good way to model for these bonds with recovery. Okay, so from here, let me now go to the spread. The credit spread is what markets observe. That's why the probability of solvency or default is risk neutral, because it comes from the market. Okay, so the spread would be what we saw earlier, is the value of the notional discounted to today. And when we solve for the probability of solvency, what we get is it's equal to this. You can solve the equation yourselves. Now, this is very interesting, isn't it? Please pay attention to this formula. What this formula is telling me is that from market prices, you can calculate the probability of solvency of countries. In fact, you can price the probability of default of countries because that's 1 minus q. That's pretty remarkable, isn't it? Can you do the same for people? No. People don't issue bonds. People don't have a risk neutral measure. For people, you have to use machine learning. Back to what we discussed earlier, you see? So this allows me to calculate the probability of default of countries if I know their credit spread. But the credit spread is there. You can use your assignment number 1 code to calculate it, right? You can actually make this work. I made these numbers myself. In 2012, that was before the Brexit situation, when other countries were having problems. You can calculate the probability of default. Here I'm assuming a probability of a recovery rate of 50%. But you could see that the probability of France defaulting was 2%. The probability of Portugal defaulting was 17%. And these are risk neutral probabilities because they are implied by market prices. That's how powerful we are. We haven't done anything today, have we? No, we haven't done anything. Everything we have done today was already done in your assignment number 1. We just wrapped it up into a context of credit, but that's it. Nothing is new. Everything you have already done. I told you you were very powerful after assignment number 1. Assignment number 1 is going to stay with us until the end of this course. It's a very powerful exercise that you did. I want you to know that. When you're powerful because of something, you need to know what that something is. Okay? Let me pause here. Is everybody understanding what I'm doing here? Is everybody, do you feel like you could do this yourself if I gave you half an hour? Yeah, you could. That's great. That's great. So does it feel good? It should feel good. You know, I don't know how much of this you knew, but now you should realize that you actually are near experts, right? So go with confidence to your next job interview if it's about credit, because you know now a lot of things about it, all right? Okay, so now let me put this into a mathematical context. And now we're going to be really powerful. For this, I'm going to go back to my Markov discussion. And especially for those who have never seen Markov chains before, I'm going to give you now a crash course on Markov chains. You know, that's my style, you know. There's courses that I'm going to, in less than half an hour, I'll give you a crash course on Markov processes. So if you already know this, you know, just make a link between what I am saying and what you already know. If you've never seen this, then try to understand what I'm saying, and then very quickly after, if you like it, try and get some precise knowledge about this beyond my fast description. Okay? All right. So this is the way to think about a Markov chain. By the way, Markov processes are just generalizations of this, but it's the same thing we already saw. Instead of working with only two possible states, credit states, default and solvency, I'm going to have a whole bunch of them. Being practical, I'm going to say I'm going to have 8. You will see why I have 8. I have 8 different credit states. And then in every one of my credit states, I have a probability of transitioning from that credit state to another credit state. And that means that if from every credit state from 1 to n, I can go to another credit state from 1 to n, I can organize all that information into a matrix. We already saw that matrices are good to organize information. And we've also seen that sometimes if the information is organized correctly, the algebraic properties of the matrix will actually work for us to understand what's going on. We saw that with option pricing. We're going to see that again with Markov chains. Okay, so let me organize the information like this. The probability of transitioning from state I to state J is entry Pij in a matrix. Okay? It's just a way to organize information. That's how you would write the information on an Excel spreadsheet. Note one thing. If I add all of the row entries, they add up to 1. That's a symmetry of my matrix. So this is not just any matrix. All the elements are positive, yes, but they add up to 1. That's going to have consequences for us, okay? A matrix like that is going to have a name. It's going to be called a Markov matrix. To the people who did not know what a Markov chain was before coming here, you're still okay. If you knew matrices, you're still okay, yes? If not, say otherwise. So you may have heard about credit rating agencies. Let me now tell you what they are. A credit rating agency is essentially a company that sells Markov chains to banks, to institutions. But hold on, I have to give you some details about I want to get into their business model, okay? So credit rating agencies are corporations whose business is to rate the credit quality of corporations, governments, and also specific debt issues. So if you want to issue a bond, you go to the credit agency and say, I want to issue a bond. What's my rating? And these companies, here are some of the names, they would issue a rating for you. Okay, let's understand that a little bit. You've seen these credit ratings. We just mentioned earlier that Goodrich was downgraded to BBB minus. That's a credit rating, okay? So S&P, Moody's, Fitch, they do that. They issue credit ratings. Let me ask a collective question. These are businesses. Who pays them? Who pays credit rating agencies? The people who are going to buy the bonds issued by the counterparties, or the counterparties that issue the bonds? Who pays them? The counterparties who issue the bonds pay them. Do you think that's a conflict of interest? Let me ask you another question. You don't have to answer that. You all go to the University of Toronto. The University of Toronto is going to give you a rating, yes? Who pays the University of Toronto to give you the rating? Your employer or you? Well, you know the answer to that. Is that a conflict of interest? What would happen if at the University of Toronto there's a special office, which is the special client office or a special student office? You go there, and if you write a big check, they give you the mark you want. Can you imagine that? Can you imagine that? What would happen? You know what would happen. Someone is mentioning 2008. I actually disagree. I actually disagree. Let's stay with the University of Toronto. What would happen? What would happen is that very quickly, a degree from the University of Toronto will be worth very little. We're going to see examples. Now that we stop working for free, we're going to see the value of businesses, and the value of businesses is going to be very difficult to express. It is true that in 2008, this was the chatter that people were talking about. Credit rating agencies, they just issue ratings for the corporations who pay them. So, of course, if you pay them more, they will give you a better rating. That's actually not what happened, and that is actually not how it works. Because companies, like University of Toronto, Harvard University, Stanford University, we know the impact it would have if we sell grades, right? So maintaining your standards is important. And that's what happened to credit rating agencies in 2008, because what happened is this. Unlike the University of Toronto, there's a published algorithm that says how credit ratings are calculated. In the University of Toronto, you cannot do that. We don't publish the exams. The exams are secret. You have to go to them, and you don't know what you're going to be asked. But in the financial sector, you can't function like that. People need to know exactly what is the rating algorithm. And what happened in 2008 is that the rating algorithms were public, and therefore they were engineered against. Many of these corporations created instruments. I'm not going to get into what they were, whether they were special purpose vehicles or typically not bonds. And they managed to go through the filters that the rating agencies have because they're public, right? So it just was perhaps a poor implementation of a model which is very hard to circumvent, which is you can't have bondholders pay for the rating. That would be a private investigator. They exist too. But rating agencies are the ones who, because they need to have so much information about you, the issuer, then they almost need to work like the way they do. Now, credit, what's the word? So Equifax and TransUnion, they are the retail version of that. And you all have a credit rating with them, so do I. I don't pay them. It's the consumers of the rating who pay them. But because of that, they need to rely on different information, and that's a different business model. It's all about data. And perhaps this is the connection between the credit trade of 1983 and the Scotiabank deal with Cencosud in 2014 or something. It's all about data, and the data you use is the data is what will define the business model, the credit quality, and the decisions that you made. And now we're no longer in the situation where markets are complete and everybody works for free. Information asymmetry is real, and it's something that we need to take into consideration. Okay, so that's now I'm going to stop that because this will quickly become into discussion about just about business, not about credit. So let me continue. But I want you to be aware of all of these issues, okay? Because they affect the data that's given, they affect the business that you have, and they affect basically everything that I'm talking about here. Okay, so let me go to the S&P rating system. Uh, they have, like I said, 8 ratings. That's why I use the number 8. And they're classified into investment grade and non-investment grade. Investment grade is at the B level. Everything above it is considered to be investment grade. Everything below it is considered to be non-investment grade. Now, I want you to understand these words in English, like likely to fulfill obligations, ongoing uncertainty, is just words. This is the credit rating that is given. These companies spend a lot of effort giving ratings to companies, but that's best expressed by the matrix that they report. And because this is what they sell, I told you earlier, these are companies that they are really selling Markov chains. That's their business. They sell Markov chains. And in the Markov chain, you cannot just sell the rating. You have to give the transition probability between one rating and another. That's something we don't do at the University of Toronto. Okay, we don't say, oh, you are a C student, but very likely you're going to be like a wonderful professional, and you're going to. We don't do that, right? Ours is just a point in time. Um, Perhaps the equivalent of that will be a letter of recommendation, which is what I write very often to many of my students. Then I try to make it's almost like that'll be closer to a Markov chain if you understand the analogy that I'm trying to draw here. Yes, but so this is the S&P transition probability matrix of a few years ago, and I want to. They said this is a footnote to this statement that I'll go back to in a minute. Let's look at this matrix that we have here. There's some things that I want to draw your attention to. Obviously, the sum of all the rows equals 1. They are probabilities, so they have to add up to 1. The last row, the default row, is if you're on default, you stay on default. So, okay, so that's where we are. And then note these two numbers that I've highlighted that I've circled in red. Do they look counterintuitive to you? They seem to indicate that it's more likely for a triple C company to be triple A the next year than if you are rated B. Is that counterintuitive? Is that wrong? What's wrong with that? What's up with that? What's up with that? Anybody finds that strange? Well, there's no reason to be strange. Markov transition probability matrices don't need to have any particular symmetries. Nothing needs to be monotone, decreasing, or increasing. If you look at the D column, yes, we expect triple C companies to be more likely to default than triple A companies. That's why we write those rows like that. The rows are organized, are sorted because of their D column value. But that's it. Everything else in the middle could be anything. For example, you would notice that typically in the diagonal you have the biggest numbers. That means that for just about every credit rating, it's most likely you stay where you were. But that's just a consequence of the measurement. There's nothing structural that forces that coincidence. Like there's nothing structural that forces this coincidence. There's several ways to explain this. It could be, for example, imagine a startup that becomes AAA. Well, when you're a startup, you're rated triple C. No one will rate you any other way. You get the lowest possible rating, and if it was a triple C minus minus minus, that's what you would get, right? So every company that becomes AAA was a startup at some point, was a triple C company at some point. Maybe that explains that number. But the fact of the matter is that we don't know, and we don't have to explain any of these numbers. These are numbers which they are calculated somehow. They could be solutions of a whole bunch of equations trying to reconcile numbers observed in the markets, and this is just the way it happens. So there's no particular symmetry that these matrices should have. Okay? But now let me go into the following question, the following calculation I'm going to do. Imagine I have my transition probability matrix. It's a one-step transition probability, so 1 year, okay? A step is a year, 1 year transition probability matrix. Let's say that I want to calculate the 2-year transition probability matrix. So the transition that I go, so the probability that I go from state I to state J in 2 years, not in one, but in 2 years, that would be what? Well, it's the probability that I go from state I to every state K, every intermediate state K, and from there onward to state J, right? And because they are conditional probabilities, and these are independent events, because if I go through K, I don't go through K prime, then it's the sum. This is what it is, right? This is basic probability theory, correct? Everybody sees that. The probability that I go from I to J in 2 years is this sum through all of the possible intermediate values I have. But this is the matrix A squared. You would recognize that this expression we have here is the expression for the entries of the matrix A times A. So what would be the transition probability matrix of, say, 10 years, 30 years, 5 years? Is A to the power n, where n is the number of years, right? By the same argument. Am I right? Is that clear? Good. So if it's clear, what's the transition probability matrix for a month, or a quarter, or a day? It will have to be a fractional power, right? Okay, next question. I write in the chat, who, oh, there's something in the chat that I haven't seen. Okay, who has not seen how to take the power of a matrix, which is not an integer power? Like, for example, the square root. Who has never done the square root of a matrix? I want to know. Write in the chat. If you've never taken the square root of a matrix, or never taken the, logarithm of a matrix or something like that. You have not. So a few people have not. Okay, so not to worry. Not to worry. I will tell you how to do that, okay? But before I do that, I want to give some context to that. I don't want this to become now suddenly a course in linear algebra. I suspect everybody finds intuitive the fact that I have powers of matrices at integer times. And then one might think that by extension, if I have intervals which are not integer, then the same power rule would work, right? So I'll get into that. The first thing I want to do is I want to show you how to take square roots of matrices, so fractional powers of matrices. Now, I suspect most of you, whatever you have seen is correct. I am sure of that. But the fact that it's correct does not mean that it's adequate. I suspect many of you have seen inadequate expressions for square roots of matrices. Okay. Typically, when this is taught in linear algebra, you're taught to do the square roots of matrices using eigenvalues and eigenvectors. I suspect that's how many of you may have seen it. I don't know. It's a wonderful method. There's nothing wrong with that. The problem with that is two things. First, that only works for matrices with eigenvalues and eigenvectors. So, for example, symmetric matrices. Markov matrices are not symmetric, so it doesn't work there. And second, eigenvalues and eigenvectors are computationally very, very intensive. So if you have to do eigenvalues and eigenvectors for a matrix of, say, 100 rows and columns, not that credit matrices are like that, but they are coming, don't worry. If you have to do eigenvalues and eigenvectors for matrices of 100 rows and columns, it's very computationally expensive. And even today, with very fast computers, It's unnecessary. There's a faster way. For most matrices, there's a faster way, and that is to use Taylor's theorem. So I have here the expression that is derived from Taylor's theorem. You would probably recognize this expression if A is a number, not a matrix. Is the Taylor expansion of the power around 1. In this case, 1 would be the identity matrix. So I don't know if you recognize this to be the Taylor expansion, but it is. You can check yourself. Okay, so trust me. This is the Taylor expansion of the power around 0.1. Because it works for numbers, it has to work for matrices. You just need that the spectral radius of the matrix to be less than 1, because then you hit a singularity. Okay? All right. That has to do also with the convergence of this. You probably have seen that if you do numerical, there are numerical considerations for the speed of convergence, and this is a formula that converges pretty quickly. If you look at the factorial numbers there, the exponent can grow fast, but the factorial grows a lot faster. So this is a power series that converges quite quickly. And of course, you can implement this for matrices, because this expression is an infinite sum, but at every step in the sum, you're raising a matrix to an integer power, which is okay. You can do that. Python can do that for you. These are just multiplications, okay? So this is a faster way and certainly everybody can do this. Everybody can understand this. Why a to the power I have squared equals a, that would be something that requires some proof. But I think even to those who have never seen how to take the square root of a matrix, this is plausible. Am I right? Okay. Okay. So I think this is understood. And now I have an exercise, something that I just to make sure that we pause for a minute. I'm going to go all the way straight, no breaks. So I'm about to finish, and then that will give me time to go to my next event. Okay, and then you'll be released earlier. So let me focus on this exercise. This exercise is actually quite. Let me read it, but it's very, very simple. So consider the following transition probability matrix for the credit rating system given. The credit rating system is in this matrix here. This is a Markov matrix. The transition from A to A is 97%, to B 3%, to C 0, default 0. From B to A 2%, from B to B 93%, so on and so forth. Okay? That's my transition probability matrix. What is the probability that counterparty B, rated B, defaults in 2 years? What's the probability? Can you do that? I give you 1 minute. I want to make sure that you understand what I'm doing. This is something very easy. So you need 10 seconds, but I'll give you 1 minute. You just multiply that row by that column. You don't have to do the full square matrix. You can do it if you want to, but because I'm only asking you for element 2, 4, that's all you do, right? The answer is 5.78%. Yes? And you could do the same thing for any other quantity. And with a computer, you can do this for 6 months or a month or a day even. Okay? Okay. Now, so now this goes especially to the people who have not seen my Markov chains before. This is the Markov model we have introduced. And this is a powerful model. This is, in fact, the model that all credit rating agencies use. So we better understand it. It's very important. And it's a credit Markov model. If I start today with a certain credit rating, I call it R naught, capital R naught. That's my credit rating at time 0. Note that a credit rating, today I know what it is. So most of the, I'm just giving a label. I'm giving a rating. Okay, like you will get a mark in this course, but it's more useful to think of a rating not as a number but as a vector, because a vector is what changes over time, right? And this process is called credit migration. So I may have a certain rating today, but in a year, I don't know what the rating is going to be. So it is going to be a probability distribution given by a certain column vector. And of course, in a year is very simple. It's just the the row that comes from it's a certain row corresponding to my credit rating now, and it's obtained through matrix multiplication of my initial credit rating as a vector, not as a number, as a vector, times my Markov matrix A. That's how I explain the credit migration for a year. It's exactly the same we have seen, exactly the same, but now I'm giving you a mathematical description of that, which actually works for any period of time that I'm going to pick. So credit migration will happen over time for any number of years and will be obtained by multiplying my initial credit state, which could be known or it could be unknown, it could be random, it could be just a vector. Whatever it is, I multiply it through the transition probability matrix to the power n, and the result will be my credit state as a vector, not as a number. This is what a Markov chain is, for those of you who did not know. That's another way of thinking of Markov chains, okay? And this is easily understood. You can, in fact, this is algorithmic. You can write this down. You can all write this down. You can program this in Python, no problem, right? Okay, so get ready for the next thing, okay? What I'm going to do now is we're going to think of credit states as distributions, not as numbers anymore. Now, this is not how the market works, right? You go to S&P, they give you a credit rating, they don't give you a distribution. At University of Toronto, when you graduate, we're not going to give, the GPA is a number, it's not a distribution. But we think of them as distributions because we don't know what they will be in the future. And the Markov model can deal with that. A Markov chain can deal with credit ratings as distributions. In fact, Markov chains, Markov processes are designed exactly to be that. All right. So let me make some remarks about Markov matrices. Remember that the sum of the rows was equal to 1, right? That means that if I remove the identity matrix, the sum of the rows will then be equal to 0. If the sum of the rows is equal to 0, that means that the determinant of the matrix we have here, the Markov matrix minus the identity, is 0. Because the sum of all of the rows equals 0. So the sum of the entries in the columns equals 0, right? Therefore, there's a unit eigenvector. There's a unit eigenvector. It's called the attractor. Every state converges to this one. When you multiply any vector by powers of A, you will converge to this unit eigenvector. You can see that because every other eigenvector will be less than 1, and then you take bigger and bigger powers, the power of the eigenvector through higher and higher powers will just kill that component. So everything converges to this one. This is an attractor. Those of you who have seen Markov chains or even Markov processes would know that. If you've never seen it before, just think that if you have an eigenvector with eigenvalue less than 1, as you take bigger and bigger powers, it just gets killed. So all those directions tend to disappear over time, and everything just converges to their projection onto this unit eigenvector, which has to exist because this determinant is equal to 0. Okay? All right. What is the you need eigenvector for a credit system. What is it? Drum roll. The default state. Obviously. What does this mean? This means that every company will go bankrupt at some point. Every country will go bankrupt at some point. I have here a graph. I have a very simple credit system. I included two non-default states, two solvency states. One has a 10% chance of default. The other one has a 20% chance of default. And what I have here is the curve that shows the probability of default over time for these states. And you can see the green one is the worst rating. It goes to 100% default probability faster, but the other one does too. They all do, and that's a property of Markov chains. They all have to converge to the attractor, and in our case, in the case of credit, the attractor is default. Okay, you will have to do something similar to this in your assignment number 2. Just remember this when I tell you what you have to do. I'll tell you what you have to do next week. Okay, but this is just an expression of that. And here I'm going to say something which this is an oversimplification. This slide requires a full course, but it's very interesting, and I'm just going to give you the summary form of it. Okay, the summary form is that something called the Kolmogorov infinitesimal generator. And it's just the following calculation. Note this: the exponential of a matrix, which is what gave us this Markov chain, is the exponential of t times the logarithm of the matrix. And we can well, this has a derivative. The derivative, we're going to think of the Markov process as a differential equation. So the derivative of this is going to be the logarithm times the matrix itself. This is what it would be if it was a number. If it's a matrix, it's the same. And that means that the time-dependent process a to the power t is really determined by the derivative of this power matrix at 0. And that happens to be the logarithm of a, because a to the power 0 is the identity matrix. And this is something that is true for all Markov processes, AT, not just for ours. And this derivative is called the Kolmogorov infinitesimal generator. And it basically says that if you know this, then you know how that entire curve is going to go. Not just for the default probability, for everything. You know how the Markov chain is going to evolve over time. This is the same as we look at interest rates. If we know the overnight rate, the short rate, then we know how the yield curve will evolve over time. This dynamic, because it's a differential equation, will tell us how things go. Here is very important that the Markov chain has no memory. In other words, what is going to happen today, the way I move today is the same way I will move a year from now. I said that the Markov transition probability matrix is constant, does not change. So the way I change now is the way I will change in the future. So this derivative at 0, this determination of my dynamics now, also tell me what the dynamics in the future will be, to the point that the Kolmogorov infinitesimal generator determines the evolution of the Markov process, Markov chain, or something else. Okay, in the case of the Markov chain, is the logarithm of the matrix. And this is something that happens, in generality. There's versions of this: the master equation, the Fokker-Planck equation, or the Langevin equation. These are different expressions of the same concept, and they give rise to more and more complicated stochastic processes, which we're not going to consider in this course. I am going to just stay with the Markov model for credit, which has given us a full description of how counterparties and credit qualities would move over time. And in particular, in the case of a very simple, trivial, almost trivial, not trivial, almost trivial Markov state that says that two credit events are enough, default and solvency, only that, then I have a very, very simple description of credit quality of my counterparties, and in particular, the credit spread is going to be essentially the probability of default. Okay. Here we saw an explicit expression earlier, but if you tailor expand that expression, recovery rate equal to 0, for example, you will get that the probability of default equals very nearly the the credit spread, and the probability of default are nearly the same. Okay. All right. So I have reached the end of my lecture. I wonder if everything was clear. If there are any questions.